Welcome to the class on artificial neural networks. This video presents the simple perceptron. So, previously we have put an arbitrary neural network into this classifier. Now what we put into the network is just one single neuron. So the input vector is applied at the input, and then we have one single neuron here, and this is then called a perceptron. So this perceptron has in general some nonlinear transformation that is applied to this linear sum over the inputs, and it's a weighted linear sum. So the input component xk is multiplied with its weight, with the synaptic weight, the weight parameter wk. And then this is the sum over all these different input components, wk, xk, summed over k. In many cases, we will use just a step function here for this nonlinear function. So we have some parameter, a prime, and a prime is this value here. And then we say if a prime is larger than theta, then the output is 1. And if a prime is smaller than theta, then the output is 0. Okay, I would like to discuss now the geometry generated by the simple perceptron. So we have here my output neuron with output y hat. It gets inputs from different neurons. Say this is input neuron xk, so there's a link, and this link has a weight, and this weight would be wk, and of course all of these different input neurons, input pixels, are connected to this output, and my output is given by g of sum over k, wk, xk. And then we said we use a threshold here so that the output is 1 if this sum, wk, xk, is larger than theta, and the output is 0 if this sum, wk, xk, is smaller than theta. So let us now consider the critical case. By critical case, I mean that the sum k, wk, xk is equal to theta. So I've already pointed out that xk is one of the components of the input, and the input as a whole can be considered as a vector. That's the input vector. For example, one pattern would be vector x mu. And now in a similar way, we can consider the set of weights as a vector w. And if we do this, then we see that the sum wk xk can be written as a scalar product of the vector x projected onto the weight vector w. And so this becomes w times x equals theta. So it's the same equation. This is just the vector notation, the scalar product, and theta is a scalar. Now I would like to just make one more transformation, and that is I will divide this by its length. So now w divided by its length is a unit vector. And I do the same division on the right-hand side, and the rest I just copy. So it's x projected now on this unit weight vector. And if you want the right-hand side, you can think of as some recaled threshold. And now let's do a little geometric interpretation. So basically the claim is that this equation here is just the equation of a hyperplane. And this is high school mathematics, and let me just remind you of how this works. So out of these input vector x, I pick two components. Say I pick component x1 and then I pick component x14. Just arbitrary, there will be many components, maybe hundreds of components. I've picked two of these. Now let's start by drawing this unit weight vector. So this would be my unit weight vector. W divided by norm of W. And now for the sake of the construction, let's consider that we continue the line in the direction of this unit weight vector. And I'm interested in multiplying this by a certain factor. So now I take a certain distance, theta divided by norm of W. So that's the right-hand side in the equation I derived. And so that's just the distance. And now let's consider what happens if I construct a plane perpendicular to this dashed line, to this dotted line. Let's pick now an arbitrary vector x that lies on this line. What is a scalar product doing? A scalar product projects x, this vector x, onto the direction of the unit weight vector. So the projection of this vector x onto the unit weight vector gives me just this distance here. Now take another of these points x. For example, this point here, it would have the same projection. That means all the points on this plane that's perpendicular to this line here, the direction defined by the normalized weight vector, all points that are on a hyperplane orthogonal to this direction of the weight vector at this distance, theta over W, have the same projection. In fact, this is the set of all the critical points. This hyperplane defines the set of all the critical points, and this right-hand side of the equation is the distance from origin. Okay, and now what we are really interested in is that for positive points, we would have something larger than theta. So points that lie on this side will have a projection onto the green line which is larger than theta over W, and points that lie on the other side will have a projection that is smaller or negative. To sum up, an equation of the perceptron amounts to a set of critical points that sit on a hyperplane at a certain distance from the origin. So let me sum up. What we have seen is that we have a single perceptron consisting of a single neuron, and we use the summed input A prime, pass it through this nonlinearity, and this gives the output. Now it's convenient to think of these conditions A prime larger than theta, A prime smaller than theta, and implement it directly by saying, actually, I move the theta to the other side, and then this is a new variable. It's the old one. A is A is A prime minus theta. And with this new variable, it's now much simpler because we can now say whenever A is positive, my output will be +1. Whenever A is negative, my output will be 0. So the discriminant function for that is implemented by a simple perceptron is this wkxk sum double k minus theta, and this imposes a linear separation. So the simple perceptron, consisting of one single neuron, simple perceptron, imposes a linear separation. It implements a linear discriminant function. Now, because we have this parameter theta, this linear discriminant function, or this hyperplane, does not go through 0. So theta is somehow a measure of the distance to the origin. But now let's look together at this equation here. Well, theta is also just a sum. So we can now increase this sum to n plus 1. Here it was n, and now we go to n plus 1. And if you go to n plus 1, then we have one more input, which I've drawn here. And this input is always -1. And now I can treat what used to be the threshold theta, I can treat as one extra weight, the weight with index n plus 1. And so these two expressions here on the left and on the right, they are completely equivalent. So in the geometric picture, I said that the perceptron, or this condition, imposes a linear discriminant function that does not go through the origin. But here theta has gone, so now it goes through the origin. Well, how is that possible? Well, it's possible because we have these n plus 1 dimensions. So we have one extra dimension. All the data lies in this data surface down here. But we have one extra dimension. And so what's going to happen is that with this extended space of n plus 1 dimensions, we implement a hyperplane that goes through the origin. And this hyperplane is completely equivalent to the hyperplane that does not go through the origin in the space of n dimensions. So let me sum up. A single layer network is called a simple perceptron. And such a single perceptron can only solve linearly separable problems because it imposes a hyperplane. It's a discriminant function that's described by a linear equation, by a separating hyperplane. For theta equals 0, the hyperplane goes through the origin. The threshold parameter, normally we have theta non-equal to 0, so it would not go through the origin, but we can remove it. And then in n plus 1 dimensions, it always goes through the origin. Now, so far I just constructed a solution that separated the positive from the negative examples. And in the next video, I will show that we can adapt the weight vector such that it finds a solution to the problem. And this optimization of the weight vector is called learning.